Now, as I said, information from early visual cortex spreads along two pathways in the brain, the ventral stream and the dorsal stream. And the ventral stream is particularly important for recognizing the identity of objects. Now, early on in the ventral stream, and this is still partially in the occipital cortex, I should mention the exact boundary between occipital cortex and temporal cortex. There isn't really a straight line somewhere in here that we can draw. So sort of one blends into the other. There is one particular area, which I have highlighted in green right here, known as the lateral occipital complex. And this part of the brain is very important for recognizing simple everyday objects. One very beautiful demonstration of this is an fMRI experiment in which participants were shown different types of stimuli. In fact, stimuli that had objects in them, and the images were of different amount of integrity. Here's what I mean. This would be a well-formed image of something. And then sometimes images would look like this. Sometimes they would look like this, progressively corrupted. And see what's happening is really the image is getting scrambled. Now, in this experiment, what they did is they recorded both from V1, so early visual cortex, part of the brain that is interested in lines and edges, and from the lateral occipital complex. Now, think of early visual cortex and look at these stimuli. Do you think early visual cortex would respond more or less to this compared all the way down to this here? Well, if early visual cortex really is about lines and edges, there are lines and edges in all of these images. So it's not too surprising that if you look at visual cortex, and this, what you're seeing here, the red line is the strength of the fMRI signal. When you're seeing the full image, you get a good response in V1. Then even when you're seeing the other pictures, you always get a big response. In fact, you get more response in these, presumably because, see, there are all these lines created by the scrambling of the image. And it makes sense. V1 is about detecting boundaries and edges. There are boundaries here that make the shape of the kitten. And there are lines here that make the shape of the kitten or whatever remains of it. And these little sort of artificial little blocky lines that you get because of scrambling the image. Now, how about the lateral occipital complex? The lateral occipital complex is a region, as I said, that cares about the identity of objects and of things. So this part of the brain, would you expect it to behave similarly? Or would you expect it to behave dissimilarly? Turns out, if you look at the fMRI signal, it's very strong for this image here. And you still get a pretty good signal here. And in fact, if you look closely at this image, you can still make out that there's a kitten in here. But then once you scramble the image enough, it doesn't really respond much. It might see some features in here that I can't see because the image is too small for me. But if you're seeing that image full screen, you might still be able to tell that there's a shape in there. But beyond that, once you've scrambled the image enough, you really don't get much of a response. And it makes sense. The lateral occipital complex cares about entire objects and items. And indeed, this area is so tightly linked to your perception of the world, to your conscious perception of the world, that if you were to suffer a damage to this part of the brain, it could lead to something known as visual agnosia. Visual agnosia is what happens when you lose the ability to recognize something through your visual senses. One very famous example of this is patient GS. Patient GS had a stroke in his 30s and presented with perfectly intact sensory abilities. So he didn't seem to have any damage, any specific impairment with respect to just sensing things, particularly in the context of vision. His language is intact, and you're gonna hear from patient GS in just a moment. His language seems to be intact. His memory seems to be perfectly intact. He's perfectly oriented. He seems to understand well what's happening around him, but upon seeing something, he cannot name what the object is. He cannot recognize an object just by sight. In fact, a typical thing that happens in these patients is that you can ask them to draw something. So for example, you can show them a model. For example, you can show them a model of this pig, and the patient could actually draw the pig pretty well. If you ask them, what is this? They say, I have no idea. And you can see here how when provided with a model, a key, a bird, a train, the patient can do a pretty good drawing, can copy pretty well what this is. So the senses, the sensation is perfectly fine in this patient. Sensation and early vision, the detection of lines and edges, is clearly fine. This patient can see very well where the edges are in this drawing, and in fact, he can see them so well that he can reconstruct them. What he can't do is look at this and say, oh, that's a key, or that's a pig, or that's a bird. However, and I'm going to point this out in a second during the next video that I'll show you, the damage in the case of this patient is in the ventral stream, which means he's unable to recognize objects by sight. If you give him an object in his hands, he can recognize it. If you were to hear a bird chirp, he could recognize that something is a bird. And on top of it, so his other senses are perfectly fine. The ability to recognize something through other senses, such as by touch, perfectly intact. And what is even more interesting is that he retains his ability, he retains his how. He retains the ability to take an object and know how to interact with it. And you're going to see an example of this in the video. So he can't name what something is, but he can pinch it and grasp it appropriately. So he can still interact with the world at the visual and motor interface perfectly fine. And this is an example of dissociation between ventral stream and dorsal stream. These kind of patients, these kind of lesions, made us understand that there are two separate parts of the brain that are interested in recognition of objects as compared to their position or interacting with them. So the context for this video is that patient GS is right here and is being interviewed by a clinician. And the clinician has just shown him the picture of an object, which happens to be a combination lock, and just asked him if he can recognize what it is. So see what happens, listen to the patient, and also, mind you, look at his hands.
Another thing happens, sometimes you get something stuck in your head.
Yeah, that's true.
Okay, so I want you to give up the telephone. It's not a telephone.
Okay. Okay.
Look at his hand.
I'm really at a loss. I can't. It just isn't making any sense at all now.
Is it bigger than a cat or smaller than a cat?
Than a cat? Well, it's probably smaller than a cat.
About what size is it?
Oh, it's about that long.
Mm-hmm. About what size is it? Telephone. Just
about yay by yay.
So this is smaller than a telephone?
Yeah.
Mm-hmm. Does it have anything to do with communication?
Yeah, because this is the numbers you gotta hook up with them in order to dial your number or something, you know.
And why do you dial the number?
Because that's evidently what that dial is for. I don't know. Yeah.
Let me give you a hint.
Okay.
See, it almost feels like he's getting some of it right. There's some part of him that knows what he's looking at, but because of visual agnosia, he just can't get to it exactly. However, you've noticed how his hands were doing the exact right motion. for interacting with a combination lock, which is a wonderful example of the dissociation between the fact that some parts of our brain, the parts that are in the ventral stream, are really important for recognizing the objects, for looking at something and saying, oh, that's what it is. Other parts of the brain, separate, are very important for knowing how to interact with our environment. And as you can see from this example, clearly his how stream, the dorsal pathway in his brain, is working just fine because he seems to be able, he recognizes the kind of motion that you would do with a combination lock. You just can't look at something and instantly tell what that is. Interestingly, the section before the video that I'm showing, the scientist was showing him, the clinician was showing him some objects and asking him to name them, and he couldn't, until he would pick them up and then he could recognize them. So it's not that he lost the ability to understand any of these objects. He knows exactly, what a combination lock is. In the case of the example I was explaining a moment ago, it was an apple. He knows exactly what an apple is. As soon as he takes it in his hand, he can recognize that it's an apple. Somehow, the link between seeing something and recognizing the identity of that something seems to be broken once you get the lesion to the lateral occipital complex and the areas surrounding it. So this part of the brain is clearly intimately linked to our ability to recognize an object for what it is. And it's intimately linked to our subjective experience of the world. Now, typically, things such as visual agnosia happen when you get a lesion to something like the lateral occipital cortex, which is what I'm showing here in green. However, there are other areas in the ventral stream which are very important for other aspects of visual processing. In particular, I'm highlighting two right here. Now, what you're seeing down here is a view of the brain from below. So if you're looking from under up towards the brain, and see this part of the brain here is still temporal cortex. So it's still part of the ventral stream. In fact, it's sort of the end, the culmination of the ventral stream. And there are two areas that are very studied because they seem to be particularly specialized for specific contents. One area, which I'm showing in red, is known as the parahippocampal place area. Now, this part of your brain seems to be particularly important for recognizing and processing locations such as landscapes or houses. In fact, if you closed your eyes and imagine walking from anywhere in your house to any other place in your house, and as you do that, imagine seeing everything that you would see, this mental activity would get that part of the brain very excited. Similarly, and I'm showing this in blue, there's a part of this gyrus right here, which is known as the fusiform gyrus, that seems to be specialized for faces. It's controversial, and I'll get to the controversy a slide from now, or a couple slides from now. But generally speaking, this part of the brain right here, highlighted in blue, seems to be extremely important for recognizing faces. In fact, this part of the brain seems to be intimately linked to your experience of seeing a face as a unit. See, patients who have damage to this particular part of the brain, they develop what is known as prosopagnosia, also known as face blindness. Now, this is a condition much like visual agnosia, except it's special for faces. Again, just like in visual agnosia, low-level vision in individuals who have this condition is perfectly fine. In fact, they can recognize most objects. It's just faces that they have a problem with. Much like patient GS, they can trace drawings, they can describe things that they see, they can see objects, no problem. Faces somehow never come together as a unit. And again, they can recognize objects. They still have biographic information about people that they know, and they recognize them through other cues, for example, by the sound of their voice or by some specific feature that they have. But simply when somebody sees a face, it doesn't come together as a unit. See, when you're looking at my face right now, you don't really see, I mean, sure, you see my eyes, you see my nose, you see my mouth, you see my eyebrows, but you don't see them as separate things. You just see the whole thing as a face. And this seems to be what doesn't happen in the case of patients with prosopagnosia. To them, a face is a nose, eyes, eyebrows, mouth, facial hair, that sort of thing. It never comes together as a face, and so they can't recognize somebody from the face as a unit. Now, it's hard to explain what this might be, but I have linked down here a video to a wonderful 60-minute episode where they discuss prosopagnosia. So if you're interested by this, please click on that link. It's wonderful. And in there, somebody who studies prosopagnosia tried this particular demo, which I will try on you. So I'm going to show a number of faces. And what I want you to do is to try to recognize them. Now, the faces are rotated. You will want to rotate your head. Don't do that. Okay, just keep your head straight and look at these images. Tell me if you can recognize them. Don't rotate your head. Just look at the figures. Can you recognize them? If you want more time, pause. And see, as soon as I turn the heads, now they become instantly very recognizable. I mean, these are all faces you've seen several times. So Hillary Clinton on the left, Kanye West, Billie Eilish. You've been staring at my face for the past hour or so. And maybe you didn't recognize it when it was upside down. In fact, you had my face in the good direction in the top right corner of your screen, just nearby my upside down face. And probably it was still hard for you to recognize. And then, of course, Michelle Obama. So this is just one example of how it might feel to have prosopagnosia. You clearly saw up here noses and eyes and eyebrows and mouths and facial hair. You clearly saw all of that. They just never clicked together as a face that has a certain identity. And this seems to be something similar to what happens to patients who have prosopagnosia or who experience face blindness. And this, again, speaks a lot to the intimate relationship between specific parts of our brain and our conscious experience. The face fusiform area in particular seems to be intimately linked with our conscious experiences of faces and the identities that these faces convey.